In the last video, we talked about how to find the the rate of change or the slope of linear functions, and we learned that linear functions have a constant rate of change or a constant slope. In this video, we're going to be discussing the rate of change of nonlinear functions. Because nonlinear functions do not have a constant rate of change, the best we can do is find something called the average rate of change. And when we find the average rate of change, essentially what we're doing is we're finding the rate of change between two endpoints, or the endpoints, of a specific interval. So let's take a look at this function down below. You'll notice that it is not a straight line, so it is not a linear function. It will not have a constant rate of change, but we can still find the average rate of change between 2 points. Here's what that might look like. The question we're trying to answer is, what is the average rate of change from x equals 1 to x equals 2? Well, what we need to do is find 2 points, one where x is equal to 1 and one where x is equal to 2. And that would be this point and this point right here. And then what we're going to do is we are going to find the rise and the run between those 2 points. So let's find the rise first. The rise goes from 2 to 4. That means the rise is 2. And the run goes from 1 to 2, which means the run is equal to 1. That means the average rate of change would be the rise over the run, which is 2 over 1, or 2. The average rate of change would be 2. Now, because this is not a linear function, we would expect that the rate of change between any other 2 points would be different. Let's take a look at another example. What's the average rate of change of this function again, but from 0 to 3? So let's use the 2 points where x is equal to 0 and x is equal to 3 and find the rise and the run between those 2 points. So the rise from 0 to 3 would be 1 to 8, that's a rise of 7. And the run would be from 0 to 3, that would be a run of 3. So the average rate of change in this case would be 7 over 3, or 7/3. This function was really nice because the points that we were asked to use were integer values and were nice small numbers. But we can find the rate of change or the average rate of change using the slope formula if we have the coordinates of the 2 points that we're trying to use. Here's an example. Take a look at this graph. You'll notice that the points have larger numbers and that the scale of the graph doesn't really make it easy for us to find the rise and the run. So let's use the slope formula to figure out the average rate of change between the intervals 1, x equals 1, and x equals 5. So what are the 2 points we're going to use? Well, we're going to use the first point where x is equal to 1. That would be this pink point right here. And the second point where x is equal to 5, which would be this second pink point right here. Now, normally we would find the rise and the run, but you can see that the scale of the y-axis is not very great for us to find the rise. So we're going to use the coordinates of those points in the slope formula to help us find the rate of change. So let's find the rate of change using the slope formula. The rate of change is going to be the second y minus the first y divided by the second x minus the first x. So let's think about what we got here. The second y value is going to be 1640. The first y value is going to be 700. The second x value is 5. The first x value is 1. A little bit of simplification here gives us 940 over 4. which can reduce to 235. So what does this average rate of change tell us in this situation? In other words, what does that slope of 235 over 1 mean? Well, if we think about the units of what's going on in this table, the y values are going to have units of degrees, and the x units are going to be hours. So this would be 235 degrees Fahrenheit for every 1 hour, right? So the meaning of this slope would be that this object's temperature on average, right? This is an average rate of change. On average, increases, since it's positive, 235 degrees Fahrenheit for every hour between 1 and 5. Hour 1 and hour 5. So remember, we didn't use any data before hour 1, and we didn't use any data after hour 5. So this is only between hours 1 and 5. During which time interval do you think the temperature showed the greatest rate of change? If we look at this graph, which interval do you think shows the greatest rate of change? Well, we know that the slope of the line indicates the rate of change. So graphically speaking, the steeper the line, the greater the rate of change. So we're going to look for the section of the graph that has the steepest line. And it appears that the steepest portion of this line is from hour 0 to hour 1. Hour 0 to hour 1. Speaking of steepness of line, we can use this idea of the steepness of the line to let us compare rates of change. Lines which are more steep have a greater rate of change than lines that are less steep. Let's take a look at this very, very, very special graph below. Look at the x and y axes. We have distance in kilometers and time in hours. So our x-axis represents time, and our y-axis represents distance. And if that's the case, then the rate of change means the change in distance, over the change in time. All right, let's look at some units. What is the units of the y? The units of the y is kilometers. So this would be kilometers. And the units of the x would be hours. And so our rate of change would be kilometers per hour. Kilometers per hour. Well, what do we measure in kilometers per hour? What can be measured in kilometers per hour? Speed. So the rate of change, or the slope, is the speed of an object. This is what we call a DT graph, or a distance time graph. And distance time graphs are used to show us the speed of an object. The rate of change is the speed of an object as it travels. So what conclusions can be drawn in the context based upon the steepness of each part of the graph? So the steeper the line, the faster the object is moving. Right? The steeper the line, the faster the object is moving. So let's just check, for example, what is the speed of an object as it moves from point C to point D? So here, again, we can find the rise over the run. The rise goes from 3 to 12. So 12 minus 3 is 9. So the rise is 9 kilometers. And then the run goes from 8 to 12, which is 12 minus 8, or 4 hours. So it traveled 9 kilometers in 4 hours. 9 kilometers in 4 hours. So let's see. 9 over 4, that's going to be 2.25 kilometers per hour. 9 divided by 4 is 2.25 kilometers per hour. The last thing we want to talk about is how to find the average rate of change if our function is given to us as an equation. Let's take a look at what that might look like. Here's an example. A hiker threw a rock off a cliff. The distance, d of t, in feet that the rock travels after t seconds can be modeled with the function d of t equals 0.46 t squared. What is the average speed in feet per second of the rock between the intervals x is 3 and x is 6 after the rock was thrown? Well, what we need is we need an xy pair for both x equals 3 and x equals 6. So what we are going to do is we are going to make a little table, and we're going to put the time and the distance, or d of t, in our table. And we're going to do the time is 3 and the time is 6. And what we need to do is we need to evaluate this function when t is equal to 3 and t is equal to 6. So we're going to find d of 3 first. Remember, 3 is the input. So we're going to put 3 in for t. And we're going to do a little PEMDAS work. And we get 4.14. And we're going to do the same thing for t is equal to 6. So 4.46 times 6 squared, and we get 16.56. 16.56. Now that we have an xy pair, we have two of them, we can use our slope formula, or we can find the change in one over the change in the other. So we're going to find the slope by doing the change in the y's. That would be 16.56 minus 4.14 over the change in the x's, which is 6 minus 3. And we get 12.42 divided by 3, which comes out to 4.14. And let's think about the units here. We have feet and we have seconds. So this would be feet per second. That means this rock, between times 3 and 6 seconds after it was thrown, is going to be traveling at an average speed of 4.14 feet per second. So we got a chance to evaluate and find the average rate of change from nonlinear functions from a graph using the slope formula. We looked at a special graph called a distance time graph and how the slope of each section of a dt graph gives us the speed of an object. And we looked at how to use the equation of a function in order to find the average rate of change by evaluating that function at its endpoints of its interval. This concludes average rate of change and the lesson notes on average rate